All right. So yesterday and the day before, I talked about condensed matter systems that were related to conformal field theories. So today we're going to go beyond conformal field theory, and in my first lecture will be just a purely condensed matter discussion. So this is going to be really seemingly no string theory at all, and perhaps quite unfamiliar to some of you. Uh, I just want to highlight some basic facts about metals and more exotic metals as they are found in experiments, and some very basic things that are not understood. And please interrupt me at any time. So that'll be my first lecture. If things go around to plan, it'll be A and most of B. And I'm not going to assume you know very much background here. So we're going to use it's a little bit of path integrals and Feynman diagrams, but not much more than that. And then there's been a lot of work in the last 3 or 4 years on trying to understand some of these metallic states using string theoretic methods, but more specifically looking at the properties of charged black brains. And I'll give you kind of an overview of that, and then try to relate to close everything together and see the current status of the relationship between the holographic point of view and the more traditional point of view. All right, so the first lecture then is no string theory at all, and a few years ago there's no way this would have been discussed in a conference like this, but let's just go on. Okay, so I'll begin with a review of Fermi liquid theory. This is just very standard material going back to work of Landau and Luttinger and others in the 50s and 60s. I'm going to give you a somewhat idiosyncratic presentation of some of the basic results, and the unusual treatment is mainly because it's the treatment that generalizes the more exotic case of non-Fermi liquids, which I will then go on to. So here's the action for a here's the action that we want to describe. So it's just non-relativistic fermions with the dispersion k squared over 2m. That's it. And the key thing, of course, there's a chemical potential, and there's some short-range interaction between them, F dagger, F dagger, F, F. You can also treat the long-range Coulomb interaction, but let's not worry about that. So if you just had the quadratic action, then what is the ground state? Well, the ground state is that you fill in all states inside a sphere of radius kf, and then above kf you don't fill them in, and at least for this free system, the kf is related to mu by kf squared over 2m equals mu. So when kf squared over 2m equals mu, this term in the energy in the Lagrangian becomes 0, and above that it becomes positive. So to lower the energy, you don't want to occupy the states outside. You only want to occupy the regime where this is negative, and that's what you do. So now there's a boundary between the occupied and empty states, and that's called the Fermi surface. So this relationship between kf and mu is not anything profound. It gets modified once you put in interactions, as we'll kind of see as we go along. But what is much more profound is the relationship between kf and the density. So in this case, what is the density of electrons or fermions? Well, you just count the number of states inside the sphere. So the number of states inside the sphere is k d dk over 2 pi to the d. Little d will always be the spatial dimension up to kf, from 0 to kf. And this will equal the charge, which I'll call Q. Q is the charge density of these fermions. So everything we'll talk about today, it'll be some theory with a global U1. That's what I'll call charge, some global U1 symmetry. Of course, in solid state physics, it's just the electron number, but when we go to holographic models, It's some global, any global symmetry which has a U1 character to it. And then you couple it to a chemical potential. You could have other non-abelian global symmetries, but that doesn't really give you anything more, because once you couple a chemical potential, the chemical potential itself breaks the symmetry down to U1. So chemical potential is kind of special to the U1 case. All right, so there's this relationship then between the value of Kf and the charge density. That's called the Luttinger relation. And a very deep theorem of condensed matter physics is the Luttinger theorem, which is that this relationship is not modified by interaction to all orders. And we'll see even in non-Fermi liquids it's not modified. It's a very, very robust relationship. And it comes from a fairly subtle argument, which is has a flavor of an anomaly type argument in field theory. I won't go through it, but anyway, okay. There's also a beautiful argument by Oshikawa, which gets this relationship from a flux piercing argument, very much like the quantization condition for the Hall conductor in the quantum Hall states. There's a similar kind of flux piercing argument where you take your Fermi liquid, put it on a torus, and pierce flux 2 pi to the center of the whole of the torus, and modulo some assumptions, then you can show that this relationship must hold. So it's a very deep relationship. It's really the heart of what metals are about. That there's a Fermi surface, and Kf always obeys this. Yes?
You said that this is related to some kind of U1 global symmetry, right?
Yes, yes.
So Q is the charge of that?
Correct, charge density.
Charge density.
Charge per unit area of volume. Yeah, depending on it.
So, I mean, charge conservation does not say anything about the Q times B has to be the same.
Q times what?
The total charge has to be, I cannot change.
Well, the total charge is infinite. We're talking about an infinite system. So everything is density per unit volume. So Q is the charge per unit volume. It's a continuously variable number. It's not an integer because you have an infinite system. Of course, the finite system, then Q jumps by integers. But we're not interested in that limit. So what's really special about the Fermi liquid is precisely the point that you can continuously vary Q and get a ground state. So you can vary so smoothly at 0 temperature and get any density you want. And this happens in a system where you don't have any broken symmetry. So in fact, I kind of conjectured a statement that if you have a quantum system, infinite quantum system, it's got a global U1, and you're able to continuously vary the charge density associated with a global U1. Then, if there's no broken symmetry, including the U1 is preserved and translational symmetry is preserved, then that system must have a Fermi surface. There are no known corner examples, at least in condensed matter, to this very general statement. So the Fermi surface is really intimately tied to the ability to smoothly vary Q, because you can just change the size of the Fermi surface and change the charge density. Another system where you can smoothly vary Q is a superfluid, where you have a Bose condensate. But there you've broken the global U1. You have a condensate, you've broken the global U1. You can also smoothly vary Q in a solid. You can compress a solid and change its density. But then you've broken translational symmetry in the solid, so on. You can try to think of examples, and this is it. Okay. So that's why the Fermi liquid and the Fermi surface are really so crucial. They're unique, essentially unique compressible quantum states at 0 temperature. Okay. So that's the non-interacting. Now I want to just give you a few results on what happens when you put in interactions, what the consequences of these are. Mostly this is not very strong. And what I've done is actually taken a chapter from the new edition of my book, and it's all on the slides that you can look up on the website. Don't worry, I don't expect you to read this, but it's there. All the words are there, and a more careful treatment of some of the issues that I'll go rather quickly through right now. So what I want you to focus on is just the colored lines, right? And I'll say in words what's actually even written here, all right, or some summary thereof, okay? So that's another picture of our free fermions. Now I'm calling them C, not F. Sorry about that. But an EK is some dispersion, which is chi squared over 2m minus mu. Okay, always include the chemical potential in the definition of the dispersion. Okay. So this forms a Fermi surface. And what I want to do now is take this Fermi surface and just look at one point on the Fermi surface and just do a simple RG argument calculation. So I take a Fermi surface and I just pick a point on it. So this is, so in terms of this Lagrangian, that surface is the locus of point where EK is 0. So where EK is 0, that's the Fermi surface. Okay, so let's pick a point on that. So you can read all that, but let's pick a point K naught. Okay. And now what I'm going to do is I'm going to take a long wavelength limit and write down a field theory. The reason I want to do that is because I'm incapable of doing more complicated calculations. I always want to have a field theory and do RG and turn the crank. So, but this big Fermi surface is a hard thing to deal with because it has zero energy excitation at large K. Whereas in field theory, the implicit assumption always is that the lowest energy excitations are at K equals 0. So let me just pick a point and work here. So then in this new coordinate system, where this is K equals 0, low energy and low momentum are the same thing. So that's all I'm going to do. So I go near this point, and now I can do a gradient expansion of everything because time and space derivatives should somehow scale together with each other. So if you expand about that point, you first get the d by d tau, which is just as before. Then in this direction, which is the x direction, you get energy varies linearly with derivative, with k. So I get a d by dx. So in the x direction, this is a chiral fermion. It's like a 1D chiral fermion in this direction. And then in the y direction, however, it's not a chiral fermion. In the y direction, the energy goes as the square of the momentum in this direction because it's a tangent to this point. So I choose y to be tangent to the Fermi surface. So that's d by dy squared. So you get this anisotropic structure with linear dispersion in one direction and quadratic dispersion in all the other directions, which is d minus 1. Okay, so there it is. And now I can add some interactions. And the first question I can ask is, are the interactions important or not? And I'll just do it in a very canonical RG way. So the first thing you want to do is take this action and see that it's actually scale invariant. You do some scale transformations. And you can easily check that if you rescale y by a factor of e to the minus L, and x by the factor of e to the minus 2L, tau by minus e to the minus 2L, and psi by this, the whole thing is invariant. Okay. I guess one more thing I forgot to mention. The reason this dispersion is a bit is really unprecedented in field theory books is if I now ask where is the zero of energy here, what energies do I have zero? The zero of energy in this coordinate system is a line. It's a parabola. Kx equals k minus ky squared. That's my parabola. So I have some Green's function, which is doesn't have a pole at a given k equals 0. It has a line where it has zero energy. That's really what makes it a little tricky. Well, that's what everything's about here. All right. So now you do this transformation. Then you add in some interaction. Just take some contact interaction. And I had to put in some flavors here. Otherwise, this would be just 0. So imagine there's some colors, flavors. Anyway, just for simplicity. And so you do this, and you figure out how the four Fermi coupling scales. And lo and behold, this is what you get. That in all dimensions greater than 1, it's irrelevant. So that's really at the heart of why interaction is not important. At low energies, they just flow to 0. Here, I'm only looking at long wavelength interactions. And they're essentially irrelevant. Just one second. But there's this, of course, can be large momentum transfer where you go from one patch to the other. And that's a little more tricky. And there's also an RG interpretation of those interactions by Shankar and by Polchinski, who have a somewhat different treatment. I'm not going to go through that, because when we get to non-Fermi liquids, this would be the better way to think about things. Yes? Well, okay, so it simply comes from the fact that I chose my coordinate system. So you pick a point on the Fermi surface anywhere you want. Okay, you pick a point. So here I know that Ek is 0. As some function of k, this is kx, and k, this is some coordinate system which measures k, and pick a point where k is 0. Then here I define this to be my x-axis. So the x-axis is always normal to the surface, and the y-axis is tangent to the surface. So I have any function that vanishes here, and then you can just do a little bit of differential geometry and say, so if it's tangent means it's constant along this direction linearly. So it has to be quadratic in this direction. The line, the tangent is the line along which the function doesn't vary. So okay, it's just a little bit of simple differential geometry, and you can convince yourself that it's got to be linear in this direction and quadratic in that direction. Okay, I mean, it's just it's true for if you have a curve and you just kiss it at the end, things vary linearly in this direction and quadratic in that. You really want me to go through it? Okay. It's
in the discussion, if you like.
Yeah, I mean, you can see that what is this direction? This direction is the gradient. So n hat, if I call this direction n hat, that's just the gradient Ek. So in this direction, it doesn't move linearly, and the gradient is in that direction. That's all. So it's linear in one direction and quadratic in the other.
And Subir, you were talking about the 4 Fermi interaction
Yes.
being irrelevant.
Yes.
I guess this might be too technical, but if I'm right, there's this famous Cooper pairing instability, though, right? Isn't
Yes.
there? So except for that.
Okay, so the Cooper pairing, your excellent question, although not what I was going to discuss today at all. The Cooper pairing comes from interactions between electrons in antipolar patches, one at the North Pole and one at the South Pole. So to see that, I have to do a more careful theory where I take one electron sitting on this side and another one sitting on the other side. And between them, you will find that there is a flow. Okay. So that's a little tricky, but anyway, that also works by this kind of RG. Yeah. Okay. Right. Okay. So anyway, if I just focus on just all electrons sitting in one patch of the Fermi surface, then near that patch, the interactions are basically irrelevant. Okay. So that means that if I look, what does this mean in practice? In practice, if I take the Green's function, which previously was just omega minus Ek, then there's going to be some self-energy, which I can now try to compute. So I'm going to go to the first, if I do to first order in U0, that's just some real function, which I can reabsorb into the definition of Ek. And those, I always assume you can always do that. So the dispersion of a particle can change because it's moving in a cloud of other particles. So those things we always assume has been absorbed into a definition of Ek. What we're interested in really is the imaginary part of this function. What's the probability that if you add a particle to the system, it's going to decay into some cloud of particles and Hall excitations near the Fermi surface. Emit lots and lots of sound modes and so on. What are called well, I guess, density fluctuations anyway. All right, let me not get distracted. Okay, so if you do the calculus, you go to second order, and this is one simple graph that you have to evaluate. So here in the notes, I actually show you how to evaluate these graphs. You can't use Feynman parameters, and you could, I suppose, but there's no relativistic invariance, and this is, I find among all my string theory collaborators, this is the hardest part, doing this something that you spend a month doing in first year graduate school in solid state physics. You spend a lot of time evaluating graphs like that. If you haven't done that, it's just, this is all incredibly hard for people who can do multi-loop, string loop diagrams. This turns out to be, in my experience, but it's not that bad. Here I've just taken a simple graph and broken it up into two pieces. First, I take this bubble. It's called the polarizability. So think of this as some, vacuum polarization diagram for interaction due to some collective boson. So this is the vacuum polarization of a Fermi liquid. So that's the very first thing you got to learn how to pi of Q and omega. And here's the steps in the evaluation. So what I do here is to evaluate in full generality is a little tricky, but we're only interested in non-analytic terms. So things that are singular at low energies, because those are the things that will give you imaginary parts. So as long as you focus on those, it's quite easy. You take this, you put the Green's functions here, and it turns out you can do the integral over the momentum in the chiral direction very easily, just by residues. So that's very simple. And when you do that, in the closed contour, you get this strange sign in the numerator. And then you can easily do this integral because that just gives you a mod omega. And this is just some simple factor by shifting. Anyway, so all the details are here. And this is the basic result. So let me focus on the physics of this result. So this tells you that for imaginary frequencies, so omega here is an imaginary frequency, the polarizability up to some constants is mod omega over qy. So what does that mean? So this is what's called the particle-hole continuum, which perhaps some of you may have seen. So can I erase this now? Oh, okay. Or, well, I can do it over here. So what I'm going to do is, what we're doing effectively when we are evaluating this bubble is you're coming in and perturbing the Fermi liquid and creating one particle and one hole. So basically what that means is you start with these states occupied and everything else empty. Then take one particle and put it up here and remove it from there. So the distance you have moved is q, and the change in energy is omega. Okay? So we're looking at the imaginary part, so we're completely on shell here. I call this k. So you have the condition ek plus q. So that's k plus q minus ek is equal to omega. That's the on-shell condition. Then there's the condition that ek should be less than 0, because you can only remove a particle from where there was a particle. And you can only add it where there wasn't a particle. So ek plus q is greater than 0. So you have all these complicated constraints. So you take all these constraints and basically have to do the integral over q, integral over k. So you take some, essentially 1, figure out the volume of the region of k where this is true. Okay, so that's a kind of a tricky calculation. Work this out. That turns out to be omega over q for small q. So what that's telling you is that if I look now in the energy momentum space, q versus omega, then and ask where is the imaginary part of this polarization not equal to 0. So there's a region in momentum space that looks like this. This is for large q, but this omega over q, this little here. So some boson or a photon. What's going on? It's perfectly fine here. Yeah. Okay, well, so if this was some boson, you looked at the imaginary part of pi, what you expect is a where was I? Yeah, what you expect is a pole at some q, okay? But what you find here is if I pick a q, so I fix momentum. If I have a particle, you'll say I can have an excitation only at energy square root of q squared plus m squared, where m is the mass of the particle. But here you get excitations all the way from 0 to q. And this line here is omega equals q. Anyway, so there's lots of phase space for creating particle-hole pairs, and it's just a matter of counting and looking very carefully at these constraints. It's one of those things that unless you spend a few days going through it, you're not going to really know where it comes from, but it's really very simple, and it's the heart of the dissipation, what's called Landau damping in a Fermi liquid. It's just the ability, there's a very large phase space for just moving particles around near the Fermi surface, from just below the Fermi surface to just above the Fermi surface. Yeah.
Just because of the linear dispersion near the Fermi surface?
Yeah, I'm sure. The curvature is also important. So if I did this if you took a flat Fermi surface, then that's actually very much like one-dimensional relativistic current fermion. If you have 1D relativistic current fermion, you know there's bosonization, and particle-hole pairs behave like a sound mode. So all of this doesn't happen in 1D, where you have effectively a flat, you don't have the curvature of the Fermi surface. So it's really tied to the presence of the curvature. There are certain papers recently by a former collaborator, Puri et al. Seem quite confused about this point, in my opinion. Anyway, so now you take this particle polarizability and then evaluate the self-energy. So I guess my advice to string theorists doing Fermi liquid theory is to just go through these, at least go through one or two of these. It gives you lots of insight. And all the integrals are here. Just experience how these integrals are done. Okay, so when you put it all together, that's the answer. The imaginary part of sigma is u squared and omega squared. So that omega squared is basically tied to the fact that the interactions are irrelevant. So when I put it in the Green's function, this is the basic Green's function. Previously had omega minus ek. And now I have a small imaginary part, which is omega squared. So this means that as I go closer and closer to the Fermi surface, the width of my quasi-particle goes to 0 even faster. So if I create a particle here, it does have a finite lifetime. It will decay into these particle-hole excitations. But as it goes closer and closer to the Fermi surface, its lifetime vanishes as the square of the distance from the Fermi surface. Because the distance from the Fermi surface is basically ek, which is linear in k, moving normal to the Fermi surface. So the lifetime of a particle is the 1 over the distance. So if I take a particle here at some momentum p, let's assume it's a circular, the distance of the Fermi surface is p minus kf. And the basic result of Fermi liquid theory is that the inverse lifetime, tau inverse, goes as p minus kf squared. Whereas the energy of that particle goes as p minus kf. The lifetime is always, the inverse lifetime is always much smaller than the energy, close enough to the Fermi surface, and that's another reason why these quasi-particles. So that's why we claim that Fermi liquid, quasi-particles are defined. But one other thing you notice from here is that this lifetime actually does not destroy the Fermi surface. You might guess that previously, you had this very simple picture. Here everything is occupied. Here everything is empty. You put in a few interactions, it's going to smear things out because the interactions are going to virtually excite particle-hole pairs. That would be your naive assumption. But that's not quite right. So interactions do smear things out, but not completely. So if I just take this very simple result for the fermion-Green's function, and then compute the number of particles in momentum k, and you just take this function with any regular function of k and omega here, and you evaluate that integral here to get n of k. Take the imaginary part of the Green's function and integrate from -infinity to 0. That gives you the number of particles It's just the expectation value of C dagger K C K. That's what n of k is. How many particles do you have in the state with momentum k? You evaluate this and you get this kind of result. So here's kf, and what you find that at kf, for free electrons, this will be 1, jump to 0. And for interacting electrons, it's still got a discontinuity. So there's something singular at kf. The kf is a well-defined quantity even for the interacting system, because there's a jump in n of k. And this is just follows from the properties of that integral. And furthermore, this kf, now you define kf by the position of this jump, and then this kf, as defined by the position of the jump, is related to the density by the Luttinger relation, which I erased. Okay, so the way we think about the system when we do these calculations, you work at some fixed chemical potential. You add a chemical potential, then you get some kf for free electrons. You add some interactions, you'll find that kf is going to change, perhaps a lot, because the dispersion is going to change at fixed mu. But the density is also going to change. And the Luttinger relation is a statement that both kf and q can change at fixed chemical potential, but the relationship between them does not change. Q is always kf to the power d with exactly the factors of 2 pi cubed and so on, with no change whatsoever. So that's the deep relation of Fermi liquid theory.
Sorry, just to make sure, kf for this purpose with the interactions is defined where n of k has a
for example, right.
I see.
Another way to define it, which is equivalent to this, is you take your exact electron Green's function, and then you say that the inverse of the Green's function at omega equals 0, k equals kf equals 0. So if you look for the solution of this equation, that give you the position of the discontinuity. Okay. So it's defined, yeah. Okay. So there's still an exact pole right on the Fermi surface.
And sorry, one last thing. The total charge which goes into the Luttinger relation is the full area, right? All the charge, not just till the Fermi surface.
Sure.
Okay.
The charge is...
charge is charge, yeah.
Well, I think it's better to think of the charge as df d mu. F is the free energy. Okay. So there's some charge which is df d mu. That's always equal to kf to the power d. That's a relationship that's... mu is nothing special. Mu moves all over the map. But unfortunately, the way we do the calculations, usually we fix mu. Well, if we fix mu, the other things are allowed to move, but they move in a correlated manner. Yeah. Yes. Yes, that's a very good point. So as we'll see, when we go to non-Fermi liquids, we'll find that the lifetime, in fact, could be the inverse lifetime can be order of the energy. So the particles are not well defined. So you could lose the very sharp nature of the particles, but nevertheless, the presence and the sharpness of the Fermi surface will remain. Yeah. Well, let's see. There's two independent things. One is the existence of a Fermi surface. Right now, I've defined the Fermi surface with discontinuity in n, but you could view this as a more general definition of the Fermi surface. So that gives you a kf, so the value of kf. That's one thing. The second issue is that when you go near kf and look at the excitation, the lifetime of the excitation becomes infinity. So everything becomes very well defined, and you have quasi-particles. That second fact is sometimes assumed to be important for the Luttinger relation, that Q is equal to Kf to the D. But that's incorrect. In many books also that's assumed, but that's not true. You can actually prove the Luttinger theorem without assuming the existence of quasi-particles. It doesn't really require it. So the quantization of Luttinger theorem is very robust. The presence of large lifetime near the Fermi surface is much less so. Okay, so let me then summarize. Uh, the lifetime is increasing, but anyway, go on. Yeah. Yeah, this is all zero temperature. I mean, you can, of course, scale things as a function of temperature, but for simplicity, I'm just making statements at zero temperature. That'll be what? No, no. So if I look at this, this is zero temperature plot. At zero temperature, if I look n of k, c dagger k, c k, for non-interacting electrons, it's just a step function, 1 and then 0. But for interacting electron, even at zero temperature, you do have some electrons above kf. You can just see this in perturbation theory. You know, there's some probability of finding an electron above the Fermi surface because they can be virtually excited there and come back to second order in perturbation theory. So it's just that they're virtual, they're not real. But that's the bare particles. But the quasi-particles, you're correct. If I talk about quasi-particles, which are excitations above the ground state, those are totally absent at zero temperature. And the quasi-particles are the renormalized excitations, and they will be only present at finite temperature, and there'll be particles for k greater than kf, and there'll be hole-like for k less than kf. Okay. So this is because these are bare particles, so they're present even at zero temperature. But the renormalized quasi-particles, you're correct. They're not present at zero temperature. Okay. Yeah. I mean, it's not the language here is, I know, very unfamiliar, but really all of you know this. You implicitly use all these facts every time you do your renormalization with Feynman diagrams and dressed electrons. It's the same thing, except it's happening on a surface rather than at one point in momentum space. Yes? I'll say that again. No, maybe I didn't say that. No, if you turn on the interaction, you get bare particles for k less than kf. But you don't get any quasi-particles. Quasi-particles requires you to inject energy above the ground state energy. Okay, yeah. So this is the vacuum. This is the number of bare particles in the vacuum. You know, here for us, the bare particles, we can take an electron and isolate it from all the other electrons. So bare particles make sense. When you're doing QED, the bare electrons make no sense. It doesn't exist. You wouldn't want to ever compute its occupation number. It wouldn't make, but sometimes it's useful to think about in those terms. So these are the bare, undressed particles, and we can separate them from the other electrons easily, so that's why we know something about them. But once they're inside the metal, there are no renormalized particles right now in the metal. In the ground state, this is the distribution of bare particles. So this is something in field theory you never compute because you don't care about bare particles, right? Yeah.
The lifetime that you wrote, that is T minus K.
Yes. Yes.
So only at the Fermi surface is it
infinite? Yes.
Other places I cannot define bare particles.
Well, so you can almost define it because the lifetime, inverse lifetime, is much smaller than the energy. So if you just say the criterion that the width of some spectral function be smaller than the average, then you can define it. So it's reasonably well defined, and it's still useful for things like the Boltzmann equation derivation and so on. Yeah. Okay, so then let me just summarize the basic properties of the Fermi liquid, which I've roughly derived. First is this Luttinger relation. Second, as I showed you, now I'm writing it in a more general way, anticipating the rest of my lectures. I'm saying here that there are low energy excitations at omega of order q. I write it more generally as saying that there are excitations. No, sorry, that's not what I meant. So here I'm saying that if I go perpendicular to the Fermi surface and create particles of whole, the energy goes as mod q. On the outside you have particles whose energy is q, and the inside you have particles whose energy is also. So inside you have holes, I'm sorry. I just wrote it in this very general way with z equals 1 because, well, that's going to define my dispersion relation. This is simply the statement that the energy, as we discussed earlier, goes linearly across the Fermi surface. Okay, now you can just take this model and compute its entropy. So that's, in this case, the problem is actually very similar to the problem of chiral fermions in one dimension. So this is again a calculation that all of you have done. When you compute the partition function of Dirac fermions, free Dirac fermions, and you conclude that C equals 1, and the free energy is pi over 6 times C. This is exactly the same calculation. In fact, you get the same factor of pi over 6 or whatever it is over here too, times the area of the Fermi surface. So for the entropy, you just take chiral fermions, you count how many there are, multiply the result for one chiral fermion that you know from your conformal field theory computation, and there you go, you get the specific heat of a Fermi liquid. Again, a very deep result is that that's essentially exact once you put in the renormalization of the dispersion, even for an interacting. So now, anticipating future discussion, I'm going to say the entropy is linear in temperature. That's exactly what happens in for a chiral fermion in 1D. The free energy goes as T squared, and these are things that you know very well. But I'm going to write T to the power 1 as T to the D minus theta over Z, just for fun, where I introduce a new exponent theta, which is D minus 1. It's not at all clear what I'm doing this, but it will hopefully become clear eventually. But let me actually try to explain this a little bit. Why am I introducing this bizarre notation? So another fact you know is that the Stefan Boltzmann law for photons in 3 dimensions is energy density is T to the 4th or something. Or in terms of entropy, the entropy of a black body is T cubed. And how would I understand that? Well, if you do the calculation, you easily see if I take a black body in D spatial dimension, the entropy goes as T to the D. Okay, so we know entropy goes as T to the D for relativistic particles. Then you say, well, let me imagine the particles have dispersion omega as K to the Z. Rather than having linear dispersion, it's some fractional power. So that's another very useful exercise in a graduate stat mech course, or even undergraduate. You work it out, you get T to the D over Z. All right, so the entropy of a particle that disperses as K to the Z in dimension D is T to the D over Z. So here I'm in say 2 dimensions. So if I have particles that disperse linearly, and so I would conclude if I use this formula without thinking, I have linear dispersion, I'm in 2 dimension, entropy should go as T squared. But no, entropy goes as T. So this means the particles are not really in 2 dimensions, they're in 1 dimension. And so what theta is, if you wish, is what's called the violation of hyperscaling exponent. It's the dimension deficit. You're in a 2-dimensional system, but the particles think they're in 1 dimension. So theta is then D minus 1, okay? So all the particles can disperse linearly in only 1 direction, and they don't disperse in the other direction. So they're effectively 1-dimensional, and the dimension deficit is D minus 1. So that's why I wrote it this way. So when we go to solutions of black brains, you'll see all of this come out. Okay. Another quantity I'll briefly consider, but since I don't have time, but I think Tadashi will certainly say much more about this. You can go in and compute the entanglement entropy of Fermi liquid. Again, I won't define it. I'm sure Tadashi will say much more about it. And what you find is this very remarkable result that the entanglement entropy doesn't obey what's called the area law. It's violated by a log term. So in 2 dimensions, the area, you mean the perimeter of the entangling region, and the entanglement entropy is P log P. And this is a basic property of a Fermi liquid, and in fact, this is believed to be exact even for an interacting Fermi liquid. All right. And it's also independent of the shape of the entangling region for a spherical Fermi surface. Okay, so then here's my summary of basic properties that we're going to use for the rest of my lectures of a Fermi liquid. This is all you really need to know now. Yes? Yes, there are several numerical studies in the past couple of years. Yes. Yeah. In the strongly coupled, yes, some limited calculations. People have taken some ansatz for the wave function of an interacting Fermi system and still found the same law.
Yes,
Yeah.
This is how you explained it to me, but still
Yeah.
let me ask you, can we try to fashion a proof for the P log P even for a strongly coupled system with a Fermi surface? Just
yes.
saying if there's a 1 + 1 d CFT, effectively it must
Yeah.
be this.
That's right. So there's a paper by Kun Yang and an unpublished thing by Max Metlitsky and maybe Tarun Grover also has. So there's proofs floating around. For some reason, they haven't quite all been published. But yes, I'm pretty sure it can be done.
Thank you.
All right, so that's end of part A, which is very idiosyncratic summary of Fermi liquid theory. I haven't said anything too radical. Yes, yet. No problem. That's why I'm here. Yeah, so again, a good question. So what can we prove is a Fermi liquid? So I think that it's physicist proofs that if you do perturbation theory, if you have weakly interacting metal with small weak interaction in some measurable way, then in all dimensions greater than 1, it's a Fermi liquid. Okay, so the free Fermi fixed point is a stable fixed point. Dimensions greater than 1. In 1D, it's never a Fermi liquid. Okay, it just always breaks down. But we are restricting ourselves to D greater than 1. For strong interactions, there is essentially no proofs. But experimentally, there are many, many systems which we know interactions are extremely strong, which still are Fermi liquids. These are the so-called heavy fermion metals. Some of the heavy fermion metals have effective masses of electrons of order 1,000. So there's a strong renormalization of the particle. The bare particle and the renormalized particle differ by a factor of 1,000. But the renormalized quasi-particles still obey everything in Fermi liquid. But clearly there are some situations where Fermi liquid theory breaks down. And people have tried very hard to figure out when. And there's actually very few. And my next slides will be precisely to describe the best understood example where it breaks down. Okay. Yes. Yes. Sure. Coulomb interaction. Well, they're long range. There's a 1/r long range Coulomb interaction that you learn from freshman electromagnetism. But that's screened. That has screening. And so effectively it's short range once you include screening. So it's basically like this. Yeah. Yeah.
You said Landau told us or something that the adiabatic principle tells us.
Yeah,
that
again, that's an assumption, of course.
That's an assumption, but why does it work? I mean, the system is strongly interacting with Coulomb forces. Somehow the presence of the Fermi surface, why does that make the adiabatic argument work?
So I tried to do the best I could in the very short argument, but why does it work? Here, this is why it works. Because the interaction scales to 0, and that's really all it is. And it's also, this interaction tells you D = 1 is special. 1D doesn't work. So you have to go to next order, and then you find some relevant.
I see. So this is the poor man's way to understand Landau's great insight, in a sense. Okay, good.
This is it.
Thank you.
Okay, any other questions? All right. I have about 10, 15 minutes. We want it. All right, so then we want a non-Fermi liquid. Okay, so the example I'm going to describe is what's called the Ising-nematic quantum critical point, and for a number of reasons, which fortuitously all seem to be coming together, and I feel there must be deep meaning to that. One reason is theoretically the best understood. We really made, it's been 20 years of work, and we think we almost have a really complete understanding of this particular non-Fermi liquid state. So it's the best understood non-Fermi liquid. Second is there's many, many experiments that show evidence for precisely this kind of nematic correlation, which I'll explain in a minute, in both the cuprate superconductors and the iron-based superconductors. And thirdly, if I get time at the very end, I'll mention some recent work of Davison and Parnachev, where out of supergravity comes this Ising-nematic critical point. So hold your breath for that. But that's a speculation, but okay, it got me excited. All right, so let me just do some real hardcore phenomenology for a minute. So here's the iron-based superconductors, some complicated structure of electrons that move in 2 dimensions, mostly on the iron. The interesting electrons are on the iron. And here's a kind of a phase diagram that people have measured. This is one of the nicest phase diagrams in a very clean system as a function of some parameter. Just think of that parameter as some pressure. So you take some density of electrons here and you apply pressure to it. And at low temperatures, you get superconductors here. So I won't say much about that. It's a relatively well understood superconductor. And here you have antiferromagnetism, which means the spins have some particular checkerboard pattern. In this case, if you look carefully, the spins are antiferromagnetic this way, up, down, this way, and down, up this way. So they're ferro in this way and antiferro in the other way. Or they could be the other way around, ferro this way and antiferro that way. And the choice between those two, which way to go up, down, which way to go up, is called the nematic order parameter. Just like a twofold choice you have to make. You have to flip a coin, heads or tails, which way you go, that's what we call nematic order. It's not nothing to do with spin. It's got to do with interactions between it. It's like an energy correlation. I'll say a bit more about, of course, say much more about it in the remaining part of my lectures. Okay. Now, so what the color? So here what I really want to focus on is this color region, and this kind of plot is common to many of the superconductors. So here you measure the resistivity, and you look at what power of temperature does it vary. So they take some logarithmic derivative of the resistivity and plot alpha. So the color is a plot of the exponent alpha. Now, another of the basic results of Landau-Fermi liquid theory, which I did not derive, but it's basically related to the square over here. The lifetime goes as t squared. The inverse lifetime goes as t squared. So it's not a surprise that the resistivity, which is some measure of the probability of scattering the electrons, should also go as energy squared, which is t squared. So that's another result of Landau-Fermi liquid theory, that alpha should be 2. And now you can see from this plot, alpha is 2 only in this little corner here. And that's, the heart of the problem. That's why we're also agog about this phase diagram, because right in the middle, alpha is 1, close to 1. And so that tells us Landau theory is completely broken down. This is some new type of metal. And that's what we want to understand. So sometimes people call it the strange metal. Okay. Yes. This one? Yes. Yeah. Yeah, these are also two-dimensional. The same. They're less two-dimensional, but they're pretty much. The many details are different from the cuprates. In particular, there's no Mott insulator here. And that's, there's been bad news for the people who love Mott insulators, who've been promoting various ideas based on Mott insulators. And so their reaction has been, these are not interesting materials, or physics here is totally different. But the evidence, I think, is now overwhelming that the physics is pretty much the same, in my opinion. Yes, that's what I'm doing. Yes, yes. But that's in a whole another story. So I'm just going to pick one story. This is just motivation now. Okay. All right. So this is a very recent measurement of the same material. They looked more carefully in this region here. And what they saw was in the region, beyond the region where your antiferromagnetism, where they call it an electron nematic. And it's really right next to the strange metal. So in the remaining part of my lecture, I'm going to assume it has something to do with the strange metal, this electron nematic. And what is this thing? Well, what they do is let me remember, so they apply a magnetic field and they measure some torque. Well, just think about it. All they're doing is measuring how some property varies as you change the angle of the crystal. Now, if this is a square lattice crystal, if you change the angle, whatever result you get looks like something like a square or almost a circle, okay? A rounded square. And this is what you see of some property that I won't describe in this region. But if you go here, before you actually become antiferromagnetic, you see this ellipse. So for some reason, the electrons decide this is better than that, and we're all going to move this way. So there's a broken symmetry. They just choose a direction of motion, okay? So if I go back, yeah. This is the other high temperature superconductor with a similar phase diagram, although there's some differences here, but near the best superconductor is very similar. And here's some celebrated results of Louis TIFR showing you the same kind of physics of the nematic order. All right. Let me describe the nematic order. So this is what's happening. You start out with a metal which has a squarish looking Fermi surface. Okay, so these are the occupied state and non-occupied states. And 90-degree rotation is a good symmetry. And then what the experiments are telling us is that just on their own, the electrons decide, because of the interactions, they're going to decide to distort the Fermi surface like this. It's going to decide that y is better than x. So we want to all be in the y, more moving in the y direction than moving in the x direction. You know, that's just like even in a magnet, that's what happens. You know, all the spins decide to be up or down. They spontaneously break a symmetry because it lowers their overall energy of how they interact with each other. So here, for some reason, we won't ask too deeply. The electrons all decide to move in the y direction, but they could equally well have moved in the x direction, and so there's a broken symmetry. So as I vary if I want to write down an order parameter, the analog of the Higgs field, now this is a real field. It only breaks a Z2 symmetry. Then it's something like this. It's C dagger K C K. You count the density of electron, and you take its quadrupolar moment, cos kx minus cos ky. So if there's more in the x direction, this will be positive. If there's more in the y direction, this will be negative. Okay. So it's not breaking invergent symmetry. It's not as if they're all moving this way, but not this way. They're just picking x or y, but they're moving both ways in the x direction and both ways in the y direction. So it's not inversion. It's 90-degree rotation symmetry. So now the question we want to ask, what is the nature of the quantum critical point? So in my first lecture, I talked about what is the nature of the critical point between a superfluid and an insulator. Now I ask the question, I have two Fermi liquids. I have this Fermi liquid, and I have this Fermi liquid. One breaks the symmetry, and one doesn't. So there has to be a special point where the symmetry is first broken. Is that point a Fermi liquid? And the answer turns out, in 2 dimensions, no. In 3 dimensions, almost. Okay, and that's what I'm going to try to describe, but I'm already out of time in my first lecture, it seems. But okay, but let me at least write down the actions. How would you answer this question? So there's an Ising order parameter, phi, and so I want to write down now a field theory. So initially, we're in very solid ground. If somebody tells me there's a broken symmetry Z2 and I have a field phi, what is Lagrangian? I immediately say, oh yes, well of course, it's just the phi-4 field theory with a v of phi that goes from this way to double minimum. And that's correct, yes. Sorry? Yeah. No. So it's sitting on, there's a square lattice. It's not sitting in the continuum. So it's, even on the continuum will be a headless vector. It's L equals 2, not L equals 1. So it chooses both y and minus y, okay? So it doesn't choose y over minus, it chooses both. So inversion is not, a vector is odd under reflection. This is not odd under reflection. It's odd under 90-degree rotation, that's all. And yeah, so it's on, and because it's a square lattice, it's not continuous. It's not a quadrupolar moment with all the 5 components. It's just one of the components of the quadrupolar tensor. like M equals 2, L equals 2 component of the quadrupolar tensor, something like that. Yeah, there's only two parts. This is, well, here's the explicit expression for the order parameter. This is a real number. It's not a vector, it's just a number. And if I rotate by 90 degrees, phi goes to minus phi. If I rotate by 180 degrees, phi goes to phi. Nothing happens. If I rotate by any odd multiple of 90 degrees, it changes sign. That's all. So it's just a scalar autoparameter with a Z2 symmetry. That's all. So anytime you have a scalar autoparameter with a Z2, so here's the phase diagram I was saying in words. There's some coupling. Here phi is 0. Here phi is not 0. And if you were a field theorist, you would say, oh, well, the theory of this, let me just skip ahead. I'll come back to that. The theory of this is the 5-4 field theory, and I'm done. Okay, and this is my first lecture. But here, there's another set of low energy excitations. There are this line of zero energy excitation momentum space that have nothing to do with symmetry, that have everything to do with having a compressible system at finite density. And you can't get rid of them, that line of zeros, because of the latency theorem. So there have to be this line of zeros every time you have a finite density. So you have to worry about those low energy excitations. Even though they're not critical, there's a lot of them. So you have to couple to them. So you write down your Fermi surface excitations, and then finally you couple them in exactly the way you might guess. Phi couples to the quadrupolar moment of C dagger C of the fermions, and there's your field theory. And okay, so there's another way of writing it. So it's kind of a mess. And now let me just go through this phase diagram, and then we can stop. So this is the phase diagram at 0 temperature. I'm tuning some parameter, and I'm going from this Fermi liquid to this Fermi liquid, where I have two possibilities for my Fermi liquid here. Now I have a quantum phase transition here, and so I can draw a finite temperature phase diagram just like my first lecture. You get the fan in between, which is controlled by the quantum critical point. Now in this case, I have an Ising symmetry. So there's a finite temperature Ising transition right here. Now, one conclusion of yours would be correct if you did ignore the fermions. If you look at this finite temperature transition, that's just the classical Ising model. The fermions don't matter at finite temperature, effectively because the Fermi surface gets rounded out by temperature effects. In other words, that's the C equals 1/2 CFT. That's what the C equals 1/2, the simplest minimal model that describes this finite temperature phase transition line, at least its static properties. Quantum mechanics plays no role at finite temperature phase transitions at low enough energies. But at 0 temperature, you have a critical point here, and your first guess would be, well, that's just the Ising model in 3 dimensions. But as I just argued, that's wrong. It's not true because there's Fermi excitations I have to worry about. And what we know that in 2 dimensions, that's a strongly coupled non-Fermi liquid. So it's really the first and best understood example of a non-Fermi liquid with no quasi-particles. And the inevitable conclusion from that is the strange metal has something to do with this quantum critical point. That's by no means accepted. Many of my best friends would shoot me if they heard me say that, but I'm pretty confident that's going to be correct. We'll see. Yeah, I think. All right, I had a whole thing about now actually analyzing this field theory. I don't know how much of that I'll be able to go through in my next lecture. That if I do that, I won't have any time for holography. So I'll find some optimal way to do it. Yes, okay. I do want to say a few things about holography, so I may have to skip the analysis of this. But it's really worked out in the notes that you can get from our website. All right, let's stop for tea then.
Questions?
While everyone
Things
thinks
like everyone's had their fill of solid state physics. I should go directly into black brains.
Oh. The crucial, you went over it quickly, sorry, but the crucial experiment which says that this nematic order must be broken, that magnetic field thing or something.
Yeah, yeah.
Sorry, could you even
Oh, you really want to learn about experiments?
even for Luddites like me, can you?
Well, actually, this particular experiment I don't understand that well. So they put a magnetic field. Here's a picture. They put a magnetic field at some angle, and they measure the torque on the crystal. Okay. Now, in this region where they say orthorhombic, you expect the torque. Now, you see how things vary as a function of the angle phi. As you go, as a phi of them, you take some fixed axis, you change the angle of your field relative to the fixed axis, and you go around and you measure the torque. So, as a function of phi, if you're sitting here, you do expect something like this, something distorted. And the reason you expect that is if you look at the magnetism, in addition to choosing up and down, it chooses x versus y. So this picture, it's up, down, up, down, up, down this way, and up, up, and down, 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 down this way, up, up, up. Or it could be the other way, this way, ferro, and that way, antiferro. So in addition to picking a direction in spin space, you have a Z2 choice for this kind of magnetism. It's not, cuprates doesn't have this complexity, but this complexity makes these systems simpler. So in this region, if you were sitting in the antiferromagnet, the crystal must be orthorhombic. It's not square anymore, it's rectangular, because this bond, you can see, may become longer than that bond, because up-down is different, has different energy from up-up. Okay? So it's become like a rectangle. So any response like this, if I go around and I vary this angle, it should have the same symmetry of a rectangle, which this thing does. Okay. Now, if you do this experiment up here, it looks like a square. It doesn't care. But strangely enough, it seems to have a region here where there's no magnetism, but there's still a distortion. So in this region, it effectively you're measuring, if you wish, the average shape of the Fermi surface. And what you're seeing in that, so this, this is some measure of the shape of the Fermi surface, or the number of electrons moving in a certain direction, if you wish. What you're seeing then is effectively in that intermediate region that the Fermi surface is, that rather than that. Of course, it has to distort while preserving the volume because of all the famous theorems I'm referring to. So it's a volume-preserving distortion of the Fermi surface. It requires a quadrupolar moment. That's all. It's like I think nuclei have such shape transitions, right? They go from, they require quadrupolar moment at some point, something like that. It's a whole, but now this is a collective system at 0 temperature. Now for the cuprates, so there's a huge literature on various nematic correlations. And of course, some people hate them and some people love them. I try to be agnostic, but I'm starting to get very convinced they're very important where the experiment. So there's this other experiment here in YBCO. This is several years ago. This was one of the earliest indications. So here they measured nu aim. So nu is something called the Nernst coefficient, some kind of response. They measured along the A axis and the B axis and look at the difference, and it certainly diverges below this line. So again, that's suggesting that there's some broken symmetry. So there's a lot of indications that, but yeah, it's not to say this is driving high temperature superconductivity, but it seems to be some residual of some very complicated physics that seems to be present at much higher temperatures and much more, and I think quite crucial for many of the transport properties. And interestingly, it turns out to definitely give a strange metal. If you work out this theory of this critical point right here, it's turned out to be a strongly coupled non-Fermi liquid. Of course, there's no superconductivity, but at least I've ignored it. You can also get signals of that.
Anything else?
Yeah. Which pnictides or cuprates?
The cuprates or pnictides.
Which one?
The one in which you showed the resistivity with
Oh, that. This one.
Yeah. So
Yeah, okay.
so at the right hand side of the dome structure, so
Yeah.
there it is that the temperature dependence is as expected from Fermi liquid theory, right?
Yeah, yeah.
So in at that particular regime, so a Fermi liquid is a good approximation.
Yes.
So that means that in that particular regime, you can actually apply BCS theory on that.
Yes. I mean, it's not weakly coupled, but yes. And I think most people would agree with that. Yes. So BCS theory, I'm pretty sure it gives you a pretty good description of what's going on here at what's called large doping region, although this is not the large doping region. Yeah, I mean, the superconductivity itself is not a mystery. It is basically adiabatically connected to a BCS superconductor. All the evidence suggests that. The high TC itself, can you compute TC and see why it's high? That's still hard to do, but that mystery is not as big as the mystery of the strange metal. I think what I believe, and I think many others do also, once you've understood this more high energy region, what it's due to, and what's going on here, the superconductivity will then follow quite easily. But it's hard to do a quantitative theory of the superconductivity, which is a very low energy phenomenon, compared to what's happening here at much higher energies first. You have to understand the red region before you get to the superconductivity, at least at the level of quantitative behavior.
I have another question. So here, all these properties, they change because of this doping, once you change your doping concentration.
So I was careful to say this turns out in this particular material, that's why it's a very nice material. There's no change in doping because arsenic and phosphorus, if you remember your chemistry, are in the same column of the periodic table, so they have the same valence. So actually all you're doing is changing the size of an atom. You're not changing the density. That's why I said it's more like pressure. There are many other systems where you're actually changing the density. But the trouble with that is that when you're changing the density, you're changing the dopants, you're also changing the degree of disorder, changing so many things that it becomes a mess. This is one of the nicest systems where you're not changing much other than the pressure. Anyway, go on. Just wanted to clarify that point. That was probably not your question.
Yeah, so my question is, I mean, maybe it's doping or from other effects also. So is it possible, like, this kind of, like, if you add pressure or if you add doping, can it create, like, other types of orders apart from superconductivity?
Absolutely. So, yeah, I mean, there's a lot of study, especially in the cuprates, in this region of charge density wave order. There's lots of interesting observations of that. And then there are observations of what happens when you apply a very strong magnetic field, and in fact, the charge density wave order seems to become much stronger. So, yeah, I mean, there's a lot of work. I've worked on it a great deal myself. And that charge density wave order is surely connected in some crucial way to the nematic order too. But I was trying my best in this talk to just focus on one thing, which is the nematic order, but that's mostly for pedagogical reasons rather than because I don't want to go into all this complexity. But okay, I imagine you feel the way I feel when I see somebody starts talking about all the different omega minus baryons and this and pions and rho mesons, and I have no idea. I lose it. Yeah, well, this is just a 7-component autoparameter. It's very simple.
Thank you.
Okay.
Anything else? If there are no more questions, let's thank Subir again. And we meet at 4:40.
Just one quick announcement, since some people are beginning to leave, no students, I hope, but anyway, if you want to leave a tip for the hotel staff, you can do that with Mansi at the registration desk, and then we'll gather it all together and hand it over at the end of the conference, of the school. Okay, thank you.
State physics for many of you. No. But, I mean, so let me just summarize what I was trying to say. So we have the state called the Fermi liquid. Its basic properties are, it's got this surface and momentum space where you have zero energy excitations. And those excitations are very long-lived, provided you're very close to that surface. And everything can be then deduced from that basic property. Then the second, I started diving into the complexity of high-temperature superconductors. But here's the summary of what I was trying to say. Just imagine, for some reason, I didn't explain why. I just gave you experimental evidence that may indeed be happening. For some reason, you have a system which is a Fermi liquid that's shaped like this, sitting on the square lattice. And the interactions between the electrons are such that they decide to distort the Fermi surface in either this direction or the other direction. So, you have electrons moving around, and for some reason it may be, if they're moving all in the same direction, they don't hit each other as much, so they all like to move as opposed to moving this way. There could be a Hamiltonian. You could imagine you could certainly cook up Hamiltonians, which preserve all the symmetries, for which the electrons all decide to, clear the traffic jam and move in the same direction, and that will lower their energy. That's all. Okay. So then, that's all I need to know. I need to know that there is a critical point between a Fermi liquid with an undistorted Fermi surface and a Fermi liquid with a distorted Fermi surface, which can be in one of two positions with a symmetry between them. That's all I need to know. Because there's a symmetry, I know there has to be a phase transition, because the symmetry is either broken or not. So if it's broken or not broken, that's where the critical point is. And then, without knowing anything further, we can just, using the same technology of effective field theory, we can figure out the theory of this quantum critical point. We don't need to know the microscopic Hamiltonian. We don't need to know anything. Somebody told me there's a transition. Somebody told me the symmetry. I know these are metals. Really, that's all I need to know. So from that information, I can write down the effective field theory, go to the low energy limit, evaluate diagrams, Feynman diagrams, in this case to 3-loop order, because Max Metlitsky was my phenomenal student who could do such things, and many others also have worked on it. And so we're starting to get some understanding of what happens at this critical point, but it's by no means complete. We just know a few things about it. And one of the hypotheses that I'm certainly spending much of my time these days is trying to relate this critical point to measurable properties in the finite temperature region. We are a long way from being able to compute such things, and that's why holographic methods could be very useful for much of this. Okay. All right. So if I'm at zero temperature in this phase diagram, you're a Fermi liquid everywhere except one point, which is the critical point here, that point RC. And now we're going to just, well, I don't think I have time to go through the theory of the point RC. I'll summarize some of the properties of this point. Everywhere other than RC, it's a Fermi liquid, which I described in my first lecture. Yeah. And then you've got an Ising autoparameter. And there's a Yukawa coupling between them, phi C dagger C. So schematically, the Lagrangian is d by d tau minus ek of C dagger C plus, d mu phi squared plus the tuning parameter, the mass parameter of phi squared, and then you have a Yukawa coupling. So this is starting to look like, some model of nucleons and pions interacting by exchange of whatever, nucleons and mesons. Yukawa's model of nuclear physics. You got nucleons and some bosons phi, and the Yukawa coupling between them. It is pretty much exactly that model. Very big difference. This thing vanishes on a surface in momentum space, not at a point. That's really the only difference. Okay, so the way you do the analysis then, just like in a Fermi liquid, you focus on one point. You zoom in on one point on the Fermi surface with linear dispersion this way and quadratic dispersion this way. You take this fermion with linear in one direction, quadratic in that. Couple it by Yukawa coupling to boson, and then you turn the field theory crank. And many of the details are in the notes, but I will just tell you what the results are. Okay, is that a Fair enough. I think it's just too much to expect that if you're going to learn Fermi liquid theory and non-Fermi liquid theory on the same day. If you haven't seen Fermi liquid before, this is just a bit much. Sure, sure. Right, excellent point. So in fact, uh, yeah, so the Z2 symmetry has to do with 90-degree rotations. So it happens, so it turns out that the Yukawa coupling here at this point will differ from the Yukawa coupling here, another patch here, by a sign. So you have to keep track of the Yukawa coupling around the different patches. And okay, so there's a lot of interesting subtlety with that. All right. Okay, so let me just tell you what in pictures what you get at the end of the story. So this is it's all, you know, really its principle. It's all here. All the graphs that you'd evaluate at least at 1-2 loop level, what you have to do, and let me just give you the final answer. So this was my summary of the Fermi liquid. The Fermi liquid has obeys the Luttinger theorem, has electrons, sharp excitations that disperse linearly around the momentum, around the Fermi surface. Entropy goes this way with theta as d minus 1, with z is 1, and the entanglement entropy is p log p. All right, so here's the quantum critical point. So if you measure the same quantity n of k, you find that it doesn't have a jump, it just has a cusp. So there's a non-analyticity at some point, kf, doesn't have a jump, has a cusp. So kf is still very well defined. You know, in principle, you can get it, although it may be very hard. But it's a sharp kf. And again, there's a Luttinger theorem relating kf to the density. Okay. That's property 1. So it's a non-Fermi liquid already because it doesn't have a jump. It's somewhat like a Luttinger liquid, but not quite. Okay. Property 2, if you look at the fermion-Green's function near the Fermi surface, you don't get poles. Broad continuum at any momentum, even right at the Fermi surface. So there's some complicated functions. The spectral function is some function of q and omega. It's a universal function as you get close to the Fermi surface. Z of 3 halves. What this means is that, see, for a Fermi liquid, if you're near the Fermi surface, the Green's function is G is 1 over omega minus K. It's just a pole. K is the distance from the Fermi surface. I'm sorry, I guess I'm calling that Q. So Q. So I can also write this as 1 over omega, just for fun, as some function of omega over q to the z, where z is 1. And this function f then has a pole at omega q. So this is for the Fermi liquid. I don't know any simple form like this, but what I can say is 1 over omega to some power, some exponent theta here, and some function here, again of q to the z. Turns out, we don't know for sure, there's no proofs. In this lonely example of a non-Fermi liquid, z turns out to be 3 halves to 3 loops. So that's probably not an exact result, but nobody's ever computed z 3 halves. And you'll see this is a bit of numerology that surprisingly plays some role in my subsequent discussion. And the other 2 properties, once you identify z is 3 halves, don't change. The entropy is still d to the d minus theta over z. Z is of course different, but it has the same scaling law, and that's one of the reasons this is a powerful way of writing it. And the entanglement entropy is exactly the same, with a prefactor that's probably different. All right. So this is our non-Fermi liquid. It's, you know, intuitively very similar to a Fermi liquid in some ways because it's got this Fermi surface. It's just that the dispersion of the excitations being not sharp, and the z is not 3/2. That's all. And it's taken 20 plus years of work by people both from particle physics and in condensed matter to all pretty much agree by many, many different methods on these conclusions. Okay. So, yes.
Does not get corrected, is it? For the Fermi liquid.
What does not get corrected?
Z, that W.
This Z, the exponent Z?
Yeah.
Yeah, that's always exactly. That we are pretty sure. We don't know for sure. This eta does get corrections, and so Max was really the first to show that eta is non-zero. With Z, he's done calculations up to 3 loops, and they found no corrections. But we don't have a proof that there are no corrections. And subsequently recently claimed that he thinks there's a 4-loop graph for which he's going to find a correction to Z. We'll see. Okay, it's probably a small correction from my experience on this problem. Yeah, let's figure out. All right, so that's it. So I finished part A and B, which is a theory of metals, according, as best as we know it. And certainly it's not it's a biased perspective, but there it is. There's another non-Fermi liquid that people have studied a great deal, and that appears in a more exotic context where you get fractionalization, where you imagine the electron splits apart into slave particles, and there's emergent gauge forces and all of that jazz. It turns out quite remarkably, if you look at the non-Fermi liquid state you get at low energies in that model, it's almost exactly the same as this one. It has some differences, but basically it's the same thing. So this theory is essentially the only example we have of a non-Fermi liquid with strong interactions in any dimension. 3, there's none. There's some very weak. Well, 1 dimension, of course, there's a million, but okay. 1D, everything is a non-Fermi liquid. Yeah. Yes, yes. Well, I mean, what we're interested in is in states with Fermi surfaces because they have low energy excitations on a surface in momentum space. And those states also happen to be compressible. So that's really my perspective all along. It just so happens that the converse may well be true, that the only compressible states have Fermi surfaces. In fact, we don't know any counterexamples, as I mentioned earlier. But that's a kind of a more general, broader claim, nothing to do with the main thread of my argument. I mean, there's no question there are Fermi surfaces in these systems. So let's study the system with Fermi surfaces. But it's quite important for the holographic view. So as you'll see in a minute, in holography, there's a million compressible phases, but almost none have Fermi surfaces. So that really sets up, the big conflict here. Who's right? Are we condensed is missing many, many examples of compressible phases without Fermi surfaces? Or are most of the holographic solutions not physical? I think that's still an open question. Yes. Yes, yeah. No, those are, you can only define a compressibility with respect to global charges. If I don't have a global symmetry, none of this works. That's really crucial. Yeah, it's all tied to the presence of a global symmetry. It's because the chemical potential, you have some perturbation, mu q, mu times the charge density. That perturbation commutes with the rest of the Hamiltonian. That's really crucial. If it didn't commute, everything would be compressible. Yeah, there's nothing special about compressibility if you don't have a global conserved charge. Okay, so let's get back to then. So here's my naive view of a CFT, free massless Dirac fermions. But now I'll think like a condensed matter physics. This is graphene. These are occupied states, and these are empty states. For you, this is the occupied Dirac C. Okay. And then that we know is dual to ADS. So how do I get a Fermi liquid? I put a chemical potential. And there it is, and now I have some occupied states, and everything I've been talking about is about this Fermi surface here, which you can do that in graphene just by turning a knob. You can add electrons up to some voltage. So now this becomes a Fermi liquid. It's not a CFT at all. So the immediate temptation then is to take this gravitational model and turn on a chemical potential. See what you get. Do you get a metal? Well, so the way you turn on a chemical potential is you take your bulk gauge field and you put a boundary condition on the bulk gauge field, which puts on a chemical potential. And then you resolve the Einstein-Maxwell's equations. Okay, you put the chemical potential, and then what you get is the solution of these equations with that boundary condition here is what's called the Reisner-Nordstrom, ADS Reisner-Nordstrom black brane. And so there's some charge, if you wish, sitting on this black brane, and that creates an electric field, and that electric field gets terminated by Gauss's law by the charge density that you have on the boundary theory. And so by Gauss's law, the electric field in the bulk is equal to the charge density. And in fact, in these models, you can show the Luttinger theorem is just Gauss's law, just telling you electric flux is conserved, and since the electric flux is charge density, you can derive in some models the analog of Luttinger's theorem. But that's also quite neat how that works out. Okay, so this is a very special type of solution, and if you look at the low energy solution in the vicinity of the brain, as was emphasized by Faulkner et al., you get this factorization, and the low energy metric here is ADS2 cross R2. So you have some metallics, some state, which is a metal, whose low energy theory has this factorization between time and space. And at each point in space, there seems to be a 0 plus 1 dimensional conformal field theory. So it's got lots and lots of low energy excitations. In fact, this is a theory that with a finite entropy per unit area, even at 0 temperature. So it has rather artificial properties. But this is what you get if you put a charge in anti-de Sitter spin. That's the first thing you get. Okay, so there was a lot of work, it still is, examining the properties of this, but I want to take a little more general perspective. So let's imagine that when you turned on a chemical potential, you were forced to turn on some other scalar relevant operator. So we just represent that by some dilaton field phi, and many people here, including Sandeep, have studied these kind of models. This also rather special. It looked rather special to me. These very particular forms of Z of phi and V of phi. But I'll try to explain it in a general perspective in a minute. So anyway, you take a more general gravitational model with additional scalar field. You can put any number of scalar fields you want. In the end, you don't get a solution that's fundamentally different, at least at low energies. So just take one and then solve the equations of Einstein-Maxwell equation of this so-called Einstein-dilaton theory with the boundary condition that there's a charge density on the boundary theory. So if you solve this and look at the low energy limit, you find that low energy metric has this particular form. And I've very sneakily written it in terms of the same exponents, z, the same symbols for now, z and theta, that I introduced when I was talking about Fermi liquids and non-Fermi liquids. And I'll show you in a minute, I have the same physical interpretation. Okay. The other thing you can say is that this is in fact modulo some systems that break additional symmetries. This is the most general solution of any gravitational model which has any kind of power law behavior at low energies. Roughly speaking, there's 3 different power laws here with dt, dr, and dx, and you can always scale one away by reparameterizing r. You get 2 left over, which is z and theta. And I've written this very peculiar way because of this basic property. Suppose someone told me that low energies, I had some gravitational theory with some metric, and that theory had some scale invariance. So the most simplest scale invariance in conformal field theory is that you say x goes to zeta times x and t goes to zeta times t. And if you impose that scale invariance, there's a two-line argument and gives you the most general metric doing that is anti-de Sitter space. But then let's imagine you want time and space to not scale the same way. So you put in this exponent z. This is sometimes called the Lifshitz exponent for completely the wrong reason, but anyway, it's stuck in the particle physics in the string theory literature. However, in full generality, you have to also allow for another exponent, which is that the metric, the proper distance itself, could transform. It need not be invariant, it could be covariant. And so I call it zeta. I also allow the proper distance to scale by a factor theta. Now, if I just give you these three lines and you do few pages of algebra, you can figure out that the most general metric that's invariant under this is this. And that's why all these peculiar functions have been written that way. And I've made some choices in the direction of r, and under this parameterization, r goes to this. Okay, just from this, so now what I've shown you so far is that if you take a particular theory, gravitational theory, at finite charge density, at low energies, it has a metric that looks like this. And my claim is that this is the most general solution. You're not going to get anything else. Many people have solved all kinds of models, and all of their metrics at low energies are of this form for some value of z and some value of theta. Yeah. Sorry, if at z equals 1, theta equals 0, this is ADS4 or ADS anti-de Sitter space.
Solution of an Einstein's equations, right?
Yeah, so this is what I showed you here. So here's your theory, and this theory is defined in terms of this alpha and beta. They have these potentials v of phi and z of phi with alpha and beta. You solve the gravitational equations. After much work, you get this value of z, which is given related to alpha and beta. So z and theta are related to alpha and beta by these equations. So that comes out of Einstein's equations. Okay. So here I'm in a sense kind of working. So there are certainly, so by choosing alpha and beta to anything you want, you can get any value of z and theta you want. So this is, right now it's the space of models is too large, but it's still interesting to just look at them all collectively, which is what I'm doing. Okay. All right. So the first point is that just knowing this much, what's on this, without even knowing the theory, I can now compute the temperature dependence of the entropy. And it just follows from like a scaling argument. All right. And how does it work? Well, let's turn on a finite temperature. Then at some distance, r equals r sub h, is going to be a black horizon. Okay. And r sub h is going to diverge as t goes to 0. So what is the entropy? Well, by the Bekenstein-Hawking entropy, the entropy is just area. Here I mean entropy per unit area. So the entropy density is just RH to the minus d. And it's RH to the minus d because the volume element in the x direction is 1 over r dx squared. So you just get 1 over r to the power d when you compute the volume from the square root of g factor. Okay. So because I wrote it this way, if I had written the metric in some other way, this would be a different power of r. I chose the metric so that the coefficient of dx squared is 1 over r squared. You can always do that by reparameterizing r. Okay, so now I want to know by what power of temperature does RH diverge as t goes to 0. Okay, so for that, I just go back to the scaling laws. T has dimension z, and r has dimension d minus theta over d. Now, temperature is just inverse time, so it has to rescale by the same. So just from that scaling argument, and this particular scaling argument, you then see you have to pick a certain zeta to make temperature equal to 1, and then you just pull out the value of RH, and when you just scaling argument, lo and behold, you get this answer. So that's why I call this thing theta. This gives you an entropy density, which is the effective, again, very much like I wrote the Fermi liquid form. So what I've shown you is that if you write, if you knew Z somehow, if you write your entropy, power law of the entropy this way, and this number you get here, theta, is always the number you're going to get here when you how the full proper distance will scale under a rescaling. And that's called the violation of hyperscaling exponent. So this theta determines the entropy, and the entropy is T minus theta over Z. Yes? In the field theory side. Here, well, yeah, I didn't go through it, but right at the critical point, we did find a scaling symmetry. We got a Z and theta. That's how we got Z and theta and so on. You know, this particular scaling function was coming from some scaling symmetry that came from the field theory. There are, you know, from that two-loop RJ analysis of the field theory, which I skipped. Yeah. Well, I haven't. We don't know what theta is here. In the field theory, theta was always D minus 1. We don't know what theta is, an arbitrary number right now. So what we are getting, so yeah, that's a good. In the field theory, if I picked an arbitrary compressible system, I got a Fermi liquid. I had to work really hard. I had to tune parameters. I found one point. Aha, at this point only, it's a non-Fermi liquid, and theta has D minus 1 and Z is 3/2. That's the only point I found. In holography, what I'm finding, I have this huge parameter space of model. I can tune alpha and beta here, anything I want, over some range. And at every point, it's a non-Fermi liquid, or it looks like a non-Fermi liquid with some strange exponent. Well, that's typical of holography. It just gets way too many critical points. And when you go to real systems at small n, most, you know, it's just a few discrete points usually. Now, they can also be in condensed matter. In this other example that I didn't talk about, when you have fractionalization, you can get a whole phase where you have non-Fermi liquid behavior, but every point on the phase has the same value of Z and theta. Z and theta are pretty constrained in all of the condensed matter model. All right, so that's, however, even in the holography, there's not, there are some constraints. So you take this metric, and from the metric, you put what's called the non-energy condition, which means you take Einstein's equation, gets the stress energy tensor, and then you put the non-energy condition of the stress energy tensor, and then you find this inequality. So you get a whole continuously varying space of holographic solutions, but all of them obey this inequality. Okay. Now, very curious fact, which got me excited for a while, and I'm still excited about it. If I now take the values that I know from field theory, for theta and Z, from field theory I know theta is 1 in 2 dimensions, and Z is 3/2. That's exactly the lower bound. This was first pointed out by Tadashi et al. In a slightly different language. That's really, so does that mean anything? Probably it does. But right now, from the holography side, we don't really know any deep reason why Z has to reach the lower bound. It seems to be somehow the preferred solution is right at the bottom of the space of allowed solutions. We have no idea. I have no idea. This is just a numerological coincidence. Maybe that's all there is to it. Okay, and you can also, once you have a metric, then you can compute, yeah.
Talk yesterday,
yeah,
when you were trying to fix gamma to agree with the field theory calculation,
yeah.
that again the values seem to be exactly the one with
Not
saturated.
exactly, but close to the bound.
I see.
Yes, yes.
I see.
Yeah, yeah. I, you know, some of the values near the edge are are as weak a coupling as is possible to get with holography. Holography has too strong a coupling. So near the edge is slightly weak coupling, and condensed matter is starting from zero coupling and just reaching the boundary of the strong coupling region. That's how I might think about it. And hopefully this is a non-zero region of overlap. Otherwise we're cooked. All right, you can also compute the entanglement entropy, and that depends on the value of theta. And again, very curiously, we picked theta equals d minus 1 for other reasons before, and for precisely that value, you get the p log p answer. And many other properties of the entanglement entropy also work out. Okay, so that's then my summary of, very short summary of much work in holography on compressible models. They all fall into pretty much, one particular value of z or theta when you get down to it, and they have these basic properties at low energies. And we don't, so maybe I just summarize and say some of the open questions from the holographic side. So one we already discussed. I mean, what we really need to understand from the holography side is there any selection principle for z and theta. There was one paper by Shagulian doing some quantum corrections and looking at tidal forces and arguing that perhaps the lower bound was in fact somehow special, but I don't understand it. Yeah, so, or, so if there isn't, then where are these examples of non-Fermi liquids and condensed matter? I mean, maybe their strong coupling is so strong and we are so dumb that we just don't know how to do the theory. And holography is telling us that they exist out there somewhere. That could well be the case. I think that's a really interesting open question that we need to resolve. We found only one example. Well, there's a whole class of examples. They all have z equals 3/2 and theta equals 1, period. Yeah, so if theta is not 1, then you don't have violation of entanglement entropy, log violation. So what is the interpretation? So, and it seems kind of hard to imagine that when theta is not d minus 1, that you have a Fermi surface. So then there's some more exotic state without a Fermi surface. Or there could be more peculiar interpretations of the type that model that Sandeep's been studying, where you're not really at zero temperature and there's multiple scales and n is appearing in kind of comfortable positions that you don't want it to appear. So we'll see. Yeah, so right now, now suppose I say, okay, I'm going to take holography only at z equals 3/2 and theta equals 1. That's it. But even then I have a problem, because right now I have no direct measurement of the size of the Fermi surface, of this Fermi wave vector. How does it have a Fermi surface, and what is its value of kf? That's what we'd like to know. And even one open question is, what is the order of magnitude of kf? So, we have a density of order n squared. So let's accept there is a Fermi surface. But then there's two possibilities. You could have density of n squared, but each kf being of order 1, but you have n squared Fermi surfaces. So that's what you would imagine in some kind of deconfined phase, where the quarks, each of which has n squared colors, all forms a little Fermi surface of order 1. And then you add them all up, the volume, total volume is n squared. Or you could imagine the quarks form baryons, or the scalars and the quarks bind to form mezinos. That's a color neutral object. There's only a few of them of order 1. And then they form a Fermi surface. That would be like nuclear matter. And then you'd get a kf of order n squared, just one or two Fermi surfaces, which would be really large. And there are differing interpretations. So this kind of state would be a deconfined state. This would be a more confined state, like nuclear matter. This would be like quark-gluon soup. Which one of these is holography realizing? Well, Gupser has claims in this direction. I have argued in some cases it's here, but they're both possible. Maybe you get both classes. And where are these classes, I don't think we understand. So one question, there has been some progress, is, partial progress. Where is KF? You could look at the density-density correlation function, and you should find some oscillations, so-called Friedel oscillations, given by scattering of fermions from here to there on the opposite sides of the Fermi surface. And those are present in any Fermi liquid. Sorry, I didn't go through that. But there's good indications that if you put in monopole operators, so you have to go really beyond classical gravity and put in monopole operators, that they have, it seems like the physics is required for KF to finally become observable. So that's a very difficult but I think important direction for future work, is to look at the effect of monopole operators. So these are e to the minus n corrections and so on. But anyway.
Anticipated that in the large n limit, these would be, the Friedel oscillations would have been this suppressed, or
well,
isn't it a surprise that they're so suppressed?
Yeah, we don't know. I mean, so let me give you. So let me just conclude actually by mentioning a very nice paper. Well, it's a very curious paper, maybe completely wrong, but certainly very stimulating, by these three just last month. So what they took, so unlike, so right now, we've been just taking this zoo of model, just writing down some theory of gravity with a dilaton and look at the whole set of possibilities. So they took a particular model, which was proposed by Gubser and Roca in the condensed matter context, but known earlier in string theory, where you just take literally the bosonic truncation of type 2b supergravity on ADS 5 plus S5. That has 3 R1 R charges, so you put 2 of them equal, and the other 3 you put equal to 0. And then you just solve the supergravity equations, and you get some metric. And then you take the low energy limit, and you can check that it is of the very general form I wrote down with theta and z. Well, you can probably hear me. So I'm actually been going pretty fast. This is my second to last transparency. You can go back and do some field theory. Well, anyway, so Gubser and Roca, so you take some complicated supergravity. So it's actually, it's a theory of this form, but the potentials are a little more complicated. They're not just pure exponentials. But supergravity being what it is, you can still find an analytic solution of the full equation. And then you look at it in the large R limit, and you find, sure, yeah, it's exactly of that form, but with theta and z having some other values. And those values are theta equals minus z and z going to infinity. If you take the metric that I wrote down before and you take this limit, it becomes this in d equals 3, three-dimensional space. So everything is finite, even though theta and z are both going to infinity. So z going to infinity is sort of this ultra-local limit where everything is happening locally. And this metric that you get out is conformal to ADS2 cross R3. So this metric here is ADS2 cross R3, and there's an overall factor of 1 over R squared. And all of these 2s and 6s are pretty much fixed by the supergravity action, which is known, I guess, to some other people, not to me. All right, but what I could do is, once I figured out this metric from their paper, I could just say, oh, theta is minus z. I have the general result as a function of theta and z. And sure enough, I get the right answers, which they also got. Entropy goes linearly with temperature. That's like a Fermi liquid. That's very exciting. But the entanglement entropy goes as P, not P log P. So that's not so exciting. And then what Parnachev has studied over the years is other properties of this solution. Looked at bosonic sound modes and viscosities and so on. And not surprisingly, like almost any gravitational solution, the viscosity is also linear in temperature. That's very different from a Fermi liquid. And you get, in a Fermi liquid, there's two types of sound modes. There's something called zero sound and first sound. Zero sound happens at higher frequencies. It's collisionless. And first sound is at very low frequencies, much smaller than T. And there you get collision-dominated sound, and they have different velocities in Fermi liquid theory. In fact, there's a relationship between them that you can find in the Landau-Lifshitz. And if you take this solution and work this out, just by solving the usual ADS-CFT type equations, you have the same velocity. So many things look kind of peculiar, although one thing is really nice: entropy, specific heat is linear in temperature. So in this particular paper, they argue that all of these things can be understood with one assumption, well, two assumptions. One assumption is that this is a Fermi liquid. Fermi surface of baryons. Kf is n to the 2/3, but the Fermi velocity is vanishing. So, in fact, this is easy to understand. If you have a density of order n squared, and you have one Fermi surface, the volume of the Fermi surface is Kf cubed, so Kf goes as n to the 2/3. So that's easy to understand. Then they claim you could also understand why the entanglement entropy is P, not P log P. And that's because the entanglement entropy in three-dimensional go as P squared, Kf squared. The formula for the entanglement entropy is Kf squared log Kf squared, Kf. And Kf squared is n to the 4/3, which is smaller than n squared. So their conjecture is that there isn't a log violation of entanglement entropy, just the coefficient is smaller than n squared. So that's why you don't see it. And similarly for the Friedel oscillations. And then the sound velocities all work out with one assumption, that this Fermi liquid is precisely tuned to be exactly at the point I've been in the rest of the cinematic critical point, but in 3 dimensions. So you can work out something about the sound velocity at this critical point in 3 dimensions. The reason is you can work it out because in 3D it's almost a Fermi liquid, the critical point. And so for some reason, it seems that, according to them, this supergravity solution just happens to find the nematic quantum critical point. So I think this is a very exciting proposal. Let's see if this is, I think this should be explored further. Okay. All right, so any further questions on, that's really the end of my discussion of holography. Just a few more general concluding remarks. All right, so let me just finish up then. So what I've talked about.
Sorry, this is
yes.
very remedial, and I think you went over it, but I should know. How does the viscosity go for a Fermi liquid? You can do it.
No, I can go over. Okay. That's by no means very simple.
Okay.
And I don't know well, I have to look. It actually diverges as 1 over temperature to the 5th power. Yeah, because collisions are so rare. And one of the curious things about viscosity is the fewer the collision, the larger the viscosity. It's really very large, but it's at very low frequencies. The phase space for the large viscosity is very small. And again, if you're exactly at the critical point, collisions become much more important, and so viscosity becomes smaller. That's why they need this also. So I think the field is evolving. I mean, this is really an interesting proposal that came out of nowhere, as far as from my perspective. Very different from the deconfined fractionalized Fermi surfaces that I had been more focusing on before. And there are other papers, but I guess what Sandeep is working on and what Steve Glupser has written in the past, it does somehow seem that many of the holographic solutions are at very special points with artificial types of scaling behavior. And so I think more work is needed to figure out where we are in parameter space and exactly what type of condensed matter system we're talking about. Okay, so, right. So the whole theme of my lectures has been looking at various quantum critical points and how they lead to new types of quantum dynamics without quasi-particles. That's the bottom line. If you want to remember one thing, remember that. And the simplest example of a system, reasonably well understood on the scale of things, where you don't have quasi-particles, are conformal field theories in 2+1 dimensions, and these have experimental realizations in ultra-cold atoms and optical lattices. And right, we are on these conformal field theories, we're at the level that we can actually make some quantitative, get some quantitative insight of quantum Monte Carlo studies of just quantum critical point of generic boson lattice models. But this is all in the context of conformal field theories. And as you've heard today, once you go to metals, it's a much more messier game with lots of really basic questions remain open, and even very recent papers that seem to be changing perspectives quite a bit. And but on the other hand, there's many experiments to be understood, and so it's an exciting field to be in. So thank you.